Acid-base equilibrium, part 6, the buffer solution. What is the definition of a buffer solution? A buffer solution contains the weak acid HA and its conjugate base A-, and we will see that not any HA plus A- form a buffer solution because the buffer solution has certain characteristics. The role of the buffer solution is to maintain the pH constant by neutralizing any acid or base added in a certain amount. So it's used to prevent the changes in the pH of a solution. A buffer solution has a certain capacity. We noted the buffer capacity, which is the amount of HCO plus or OH minus that can be absorbed by the buffer system without change of the pH or with a slight change of pH. The dilution did not affect the pH of a buffer solution. Suppose we have HA plus A- and we make dilution. If the pH of the solution changed, so this is not a good buffer. The buffer solution should not be affected by dilution. The buffer solution or the buffer system has many applications found in nature, especially in blood. The normal pH of a human blood is 7.4. So some people suffer from alkalosis when they have severe anxiety. Alkalosis is a condition in which the pH of the blood is too high. And the opposite condition, a blood pH lower than 7.4, is called acidosis. So in this case, in the case of alkalosis and acidosis, the person should take medicinal drug containing buffer system that maintain the pH around 7.4. Buffer system has also other applications. Some chemical reactions proceed only at a certain pH, and many household and cosmetic products need to control their pH value, such as shampoo, to counteract the alkalinity of the soap and to prevent irritation, and also in the baby lotion to maintain a pH around 6 to prevent the bacteria multiplying. Buffer solution concept. Consider, for example, a mixture of acetic acid and its conjugate base acetate. So what is the pH of the solution when we mix these two species? According to Henderson formula, pH equal pKa of the couple acetic acid acetate plus log acetate at equilibrium divided by the concentration of acetic acid at equilibrium. In this type of formula, the pKa has a greater effect on pH than the log ratio concentration. If, for example, the ratio, if acetate is greater 10 times than acetic acid, so the pH will increase by 1 unit. For this reason, the pKa has more effect on the pH. By adding HCO+, we have in the solution acid and base So we will have reaction between the acetate and HCO plus to give acetic acid and H2O. K of this reaction is equal to the concentration of the product divided by the reactants at equilibrium. So Kr equal 1 over K equal 10 to the power 4.7. Kr is greater than 10 to the power 4, so this reaction is quantitative, and practically HCO plus in the solution or HCO plus added will be removed by reaction with acetate. But the concentration of acetate will decrease, that of acetic acid will increase, but the log ratio would not affect greatly the pH, or the pH will be slightly changed. What would happen when we add OH minus to the buffer solution? In this case, the acid will react according to the following reaction, and K of the reaction is equal 1 over Kb of the coupled acetic acid acetate equal Ka over Kw equal 10 to the power 9.3. K of the reaction is greater than 10 to the power 6. That means the reaction is complete. And in this case, the OH minus will be removed by reaction with the acetic acid. But the concentration in the solution of acetic acid will decrease. That of acetate will increase. So the ratio will be changed, but log ratio would not greatly affect the pH, or the pH will be slightly changed. So this is an example of a buffer solution, acetic acid acetate, that consume a certain amount of HCO plus added or certain amount of OH minus added to maintain the pH constant. Calculation of the pH formula of a buffer solution. Consider a solution containing a weak acid HA, where the concentration is Ca and its conjugate base A minus of concentration Cb, and A minus is provided from a salt NaA. To note that when we mix HA and A minus in the solution at T equals 0, we have dilution effect. So we have to calculate the new concentrations in the solution at T equals 0 after dilution. We suppose that Ca and Cb are the initial concentrations in the solution of HA and A minus respectively after dilution. So we follow the steps to find the pH formula. Thus, first, what are the species present? We have HA that release A minus and HCO plus. We have Na plus and we have A minus. The presence of HCO plus indicate the presence of OH minus, and we have the water molecules. Second, the principle of the electroneutrality. The quantity of charge positive is equal to the quantity of charge negative. So 1 HCO plus 1 Na plus equal 1 A minus plus 1 OH minus, and to note that these concentrations are the concentrations in the final solution. Third, the principle of conservation of species. We know that HA of initial concentration will dissociate to A minus, and A minus will dissociate to HA. So, in the final solution, we have the mass conservation, or the HA concentration in the solution plus A minus in the solution is equal Ca plus Cb. To note also that HA dissociated to A minus will dissociate to HA. So practically HA in the solution and plus A minus in the solution is equal Ca plus Cb. The reactions involved in this type of solution, we have the autoionization of water. We neglect in general this autoionization in most cases, and we have the dissociation of HA to A minus, so HA plus H2O gives HCO plus A minus. One can write this reaction, the dissociation of A minus to HA, this is the same. If we write A minus to HA, we write A minus plus H2O, that gives HA plus OH minus. So this is the same. When we write HA in water, we work on Ka of the couple. When we write A minus in water, we work on Kb of the couple. So what are the relation involved? We have Kw HCO plus times OH minus concentration equal 10 minus 14. And we have the Ka of the couple HA A minus equal A minus concentration HCO plus concentration divided by HA concentration in the final solution at equilibrium. Since NaA is a strong electrolyte, no value of Ksp given for NaA, so it's a strong electrolyte that will dissociate completely to Na plus and A minus. In this case, Na plus in the solution is equal to Cb. We suppose in our course that the solution is not very diluted, so we neglect the autoionization of water. If the behavior of HA and A minus is not given in the exercise, we suppose directly that HA is weak acid of weak behavior and A minus is a weak base of weak behavior. The quantity of charge positive is equal to the quantity of charge negative. We can neglect HCO plus with respect to Na plus, since HCO plus is provided by the dissociation of HA, and HA is a weak behavior. By the same way, we can neglect OH minus with respect to A minus, since OH minus is provided by A minus in the solution, and A minus is a weak base of weak behavior. So we obtain Na plus equal A minus equal Cb. The principle of conservation of species, HA in the solution plus A minus in the solution equal Ca plus Cb. And since Na plus is equal A minus equal Cb, so A minus equal Cb, in this case HA will be equal to Ca. So in the final solution, we have A minus concentration equal Cb and HA concentration equal Ca. So we apply Henderson formula deduced from the expression of Ka and pH equal pKa plus log base at equilibrium, so plus log Cb, divided by acid at equilibrium, so divided by Ca, and this is the relation of a buffer solution pH equal pKa plus log Cb divided by Ca. To note that this formula is obtained, we suppose that the autoionization of water is negligible, and we suppose that the acid and the base which are weak, have weak behavior. Preparation of a buffer solution. We have three methods. Method 1 is to mix the weak acid HA directly with its conjugate base A-. Pay attention when mixing HA and A-, we have dilution effect, so we have to consider the new initial concentration in the solution. We noted Ca and Cb respectively. In the previous slide, we proved that the formula is pH equal pKa plus log Cb divided by Ca, and this formula is applied in two conditions. First, we neglect the autoionization of water. Second, we suppose that the acid and the base have weak behavior. What is the meaning of weak behavior? That means the initial concentration of the acid should be greater than 100 Ka of the couple, and the initial concentration of the base we used should be greater 100 times than Kb of the couple HAA-. So pH equal pKa plus log Cb over Ca can be applied if we have these two conditions. To note, for the buffering capacity of the solution not to be low or negligible, the Ca divided by Cb ratio should be between 0.1 and 10. So a buffer solution, a good buffer solution, should have a value of pH which is between pKa of the couple HA minus 1 and pKa of the couple HA minus plus 1. So the ratio of the concentration we used in the lab, the ratio Ca over Cb, should be between 0.1 and 10. Suppose a student use a ratio Ca over Cb less than 0.1 or a greater than 10. In this case, we will have in the solution HA plus its conjugate base, but this solution could not behave as a buffer solution. The best buffer effect is when the concentration of HA in the solution is practically equal the concentration of A- in the solution. So A- equal HA, in this case the pH equal the pKa. So the best buffer solution prepared from a couple HA A- is that has a pH equal pKa of the couple. The pKa value of the weak acid used in the buffer solution should be as close as possible to the value of the desired pH. Suppose we want to prepare a buffer solution of pH 4. It's better to consider a couple HA A- of pKa around this value of pH 4. In other words, if you want to prepare a buffer solution at pH equal 4, you could not take a couple HA A-, for example, that has a pKa 6. The value of pKa of the couple we used in the buffer solution should be close to the pH of the buffer solution. The second method of preparation of a buffer solution is to react a weak acid HA with the strong base OH-, and the strong base should be limiting in order to convert a part of HA to A-. So by this way, in the final solution, we will have HA remained and A- formed. consider V0 of HA of concentration C0 plus NaOH of concentration Cb. So the question, what should be the initial volume of HA and the volume of Vb added in order to prepare a buffer solution of known pH and V total? So what would happen when HA is added to OH-? We will have a reaction complete or quantitative HA plus OH- that gives A- plus H2O. At T equals 0, the initial number of mole of A equals C0 V0. The initial number of mole of the base is equal C base times V base added. A minus at T equals 0 is equal to 0. The reaction proceeds till T equal infinity, and we said that the OH- should be limiting. So the number of moles of HA at infinity equals C0 V0 minus Cb Vb. OH- is limiting, so we have epsilon, and A- formed is equal to the limiting OH- is equal to Cb Vb. So in the final solution now we have HA plus its conjugate base A-. So we will have exchange between A- and HA. But since HA and A- are supposed weak acid and weak base with weak behaviors, so this reaction between HA and A- is therefore limited. So in the final solution, the number of moles of HA equals C0 V0 minus Cb Vb, and the final number of moles of A- is equal to Cb Vb. pH, we apply Henderson, pH equal pKa plus log A- at equilibrium divided by HA equal pKa plus log Cb Vb divided by V total divided by C0 V0 minus Cb Vb divided by V total. So the pH is equal to pKa plus log Cb Vb divided by C0 V0 minus Cb Vb. And we have other equation, V total is equal to V0 plus Vb added. So we will have two equations of two unknown. The unknown are V0 and Vb, and therefore we calculated V0 and Vb. The method number 3 is the reaction between the weak base A- and we add a strong acid HCO+. So the reaction between A- and HCO+, we follow the same strategy. The strong acid should be limiting in order to convert a part of A- to HA. So in the final solution, we will have A- and HA, and we follow the same calculations. Buffer capacity. By definition, the buffer capacity of a buffer solution is the amount of acid or base that can be added to the buffer without destroying the pH of this buffer. In general, the buffer solution, the buffer capacity, increase when the concentration of the buffer components increase. In other words, if you prepare a buffer solution from HA and A-, as you consider HA and A- more concentrated, This will increase the buffer's capacity so we can add more acid and more base without changing or without destroying the buffer. As the ratio of the concentration base to acid approach to 1, the ability of buffer to neutralize both added acid and base improves. The buffer that needs to work mainly with added acid generally have base concentration greater than the acid concentration. So for example, if you want to consume HCO+, you take the A- concentration of the buffer greater than the concentration of HA of the buffer, since A- will react with the acid added. And the buffers that need to work mainly with added base should have HA of the buffer greater than A- of the buffer.